Code, and today we are looking at another cup of code. We are talking all things database transactions or relational database transactions. We want to unbundle what ACID principles are, how we can apply them in our day-to-day implementations with database interactions, and see how we can improve our database querying as well as interactions. So we're going to talk about all things as principles, define them, and then dig down into the nitty-gritties or the deeper details of what they are. So without wasting any of your time, let's get right into it. I'm going to see the explanation and also do the queries. So please do stay tuned. And for the returning subscribers, welcome back, and we hope that you do enjoy this tutorial. If you're new, please do like and subscribe, and basically stay tuned for more coding Spring Boot database Angular tutorials, and we will showcase a lot more projects in this channel. So yeah, with that being said, let's get right into it. So ACID principles, what are they? In essence, they are a set of principles that ensure reliable processing in database systems, particularly in relational databases. These principles guarantee that database transactions are processed reliably, even in cases of errors, power failures, or other issues. So this is essentially a safe, a fail-safe mechanism for all our database interactions to ensure that any of our transactions that we perform within our databases, they actually can be successfully completed, or they can be rolled back in instances of failures, or they can be persisted into our database reliably and with the intended state, or with the intended queries that we have within our transactions. So if there's any error that happened within our transaction, that transaction can basically be rolled back and no partial commits can be taken into consideration. So the database will not perform any of the queries that we have within our transactions in cases of issues and failures. So if a transaction managed to run through successfully and we happen to run on a external failure, let's say maybe power failure within our servers or things like that, network issues, if that transaction managed to get into or managed to complete rather, then that particular transaction can persist permanently to our database, and we can have the data available to us whenever our servers come back up, and we can basically interrogate as to which transactions were successful and which ones were not successful and things like that. So that is the essence of the ACID properties that we can set up within our implementations and applications to have more reliable data snapshots at any given point in time. So let's get right into the properties of actual acidity of a database. So we're going to start with the first element, which is atomicity. And atomicity is essentially a transaction is treated as a single logical unit of work, which means everything is tied as one piece of work, which should be successful or either it should just fail. So either all operations within the transaction are completed successfully or none are going to be committed in essence. So if any part of the transaction fails, the entire transaction fails, and the database is left unchanged, which means the database won't be touched, no change will be committed. If there's an insert statement within our transaction, if there's an update statement or update query in our transaction, none of those will persist in the database. They will be rolled back as if nothing ever happened in the database. And this ensures that no partial updates are made within our database, no partial insert is made in our database, so that we keep the data as consistent, as reliable as we can be. So this the atomicity is the essence of making sure that our transactions is either going to be fully successful or fully fail and rolled back with that particular result. So let me just jump into a query so that you can see what we mean by this piece of work. So let's jump into our dbeaver. We are using Postgres, so and we have our Postgres running from a container, Postgres container that we have on our Docker Hub over there. So this is one example of atomicity. So we're going to execute this transaction to see what is going to happen here. So we're going to begin transaction, and in this begin transaction, we have a select of a entity account, and that particular entity account is with the ID 2, and we want to perform an update of entity account to set the balance to 5,000 with the ID is 2, and after that we want to see the select after this particular update, and you will see that instead of us committing the transaction, we'll basically roll back, which means we don't want any change to basically happen within our transaction. We don't want any change to be persisted into the database, and then we will have a look after the rollback and see what that record looks like, and we will basically have the end transaction over there. So let's run this transaction which has a rollback, and we'll see that nothing should be touched in the database. So we'll see the original record here, we'll do the update here, then we will basically see the record after the update statement, and then we'll do the rollback and also see the results after the rollback. And basically this result and this result should be the same, and only this one should basically show us these updates over here. So let's run this and basically have a look. So I'm going to do that. I'm going to run this statement, and you will see we have the first select, which is this select right here, and you see that the balance is 2,000 right here, and then we did the update, and then let's see the second select statement is this result right here, and that balance is 5,000, and that's the select after the update. And this was, remember, this is uncommitted change, so it's just a select after the statement, and we basically see the balance is 5,000, and then we executed the rollback, which means this select should give us the 2,000 back. Let's go to the third one and see what that looks like, and you can see that the select is giving us 2,000, which means the whatever transaction that whatever query that ran before this rollback, it was basically not taken into account, and we can basically do a select after the rollback, and you'll see that there is no impact that was done. So query 1 and query 3, or the first select and the third select, they have the same balance, or which means or the same data rather, and basically that is what we're going for, what we wanted to achieve, that if there's any failure within our transaction, it's either the transaction is going to fully commit or fully roll back. And we can see by proving that the first select on the first tab here, we have 2,000, and on the third one, we still have the 2,000, which means with the rollback, nothing happened to the database, nothing was touched, nothing was updated. But if we change this to then say commit, we can choose to say commit or commit transaction. It's the same thing, doesn't really change anything. So let's run this particular transaction and see what that looks like. And you can see updated row 1, begin, and that's basically the query. This is just the stats. So we'll go to the first tab. First tab, you can see that the balance is 2,000, and we updated that to 5,000. And then on the second select, which is this one, let's have a look at that. Second select is 5,000, which is fine because it's after our update or modification. And then the third one is the 5,000 as well, which means the transaction committed as we intended it to commit, and basically we have the expected results just like that, and the stats is basically happy with our results. So query 2 is basically aligned with query 3, which means our update went through successfully. And this is the atomicity that we are talking about, that it's either the transaction is going to fully commit, or it's going to fully roll back based on a failure or a particular issue happening over there. So let's jump into the next one, or just take a look at the definition once more. So a transaction is treated as a single logical unit of work. either all operations within the transaction are completed successfully or none are basically committed. And that's basically what we saw with the atomicity over here. So let's just copy this query so that I can basically add that query the into our repository. So if you want this particular repository, it's available in the description down below. Please do check that out, and you will have all these queries also available. And you can just change this to your particular database or table, and you can basically be around with the queries and see how you can achieve the same results with these particular principles. Now moving on to the consistency. Let's go to consistency real quickly. So consistency is basically a transaction must take the database from one valid state to another valid state. So this means that any data written to the database must comply to all predefined rules, such as constraints, triggers, or any combination of conditions that maintain data integrity. So you want to make sure that all the relationships that you've established across your database tables, all of those are followed, and they are the predefined rules of how your database is structured, and that has to always be followed according to those particular rules. And if anything is out of sync, then you don't want those transactions to basically persist. You don't want them to commit into your database, because then it uh, it basically comes or it compromises your data integrity in a way. So let's put it that way. It compromises data integrity. It means your data is no longer reliable because you cannot draw data that is basically informative in terms of how your application is performing, or what data is honestly coming through and is being processed the way that you or your rules have been defined. So let's go into the consistency and see how that particular principle is achieved in transactions. So we're going to go back to our dbeaver, and you will see that we have a transaction over here. For consistency, we begin a transaction, we select all where account the entity ID is 1, and we basically do an insert, and you'll see that we have values that we're inserting there, and we basically have another select before we commit this transaction, and then we commit everything that we just did, and then we do a select again to see if this insert went through for our entity of ID 1. So you can also play around with the tables that you have in your database, change all of these, do an insert, do an update, and you will basically achieve the same. So before I run this transaction, I'm just going to remove this ID column here, that value for the ID. I'm going to remove it so that you will see what this transaction will do, and I'm going to run this transaction, and you will see now I'm having an error on my transaction. Error: null value in column account type ID of relation violates not null constraint. So if you can look at the failing row contains, these are the details that have been shared to me. So I have, which means in my table I have 5 columns, 1, 2, 3, 4, 5, and because I'm adding 4 values here, as you can see, I'm adding 4 values over there, and the last value now is assumed to be null, and that particular column is the account type ID, and account type ID is not supposed to be null according to the rules that I've already predefined for that particular column. So it means my transaction will not persist because I am not following the predefined rules as explained over here. So all predefined rules, such as constraints, triggers, or any combination of conditions that maintain data integrity. So I need to make sure that every query within my transaction is it abides by the rules, and it basically conforms to the predefined rules, and that particular transaction will then run through successfully. But before that, nothing will persist into the database. So I'm going to put back the default so that this is an auto-generated ID, so the ID will be auto-generated, and then I'll set the amount, and let's just change this to something like let's say 33,000, and then maybe let's make this something like 10,000, something like that. And then now I'm going to rerun this particular transaction, and if you execute that, you will see that transaction is ignored until end of block. Let's see, why is that not being taken into account? Because everything now is fine. Let's see, let's run that again. Let me run that. Let me just say skip all, then begin transaction. Let's see. Now this is just my dbeaver acting up. Let's run that. Right, so now my dbeaver is back, and as you can see, my transaction now ran through successfully, and it has 3 selects, 1, 2, 3. So we're gonna look at the first select. Let's go there. You will see that the first select has select all accounts where entity ID is 1 and all these entity ID is 1, and we can see that there's a balance 6,000, there's a balance 45,000, and there's a balance of 5,000. And then we did a insert over here which ran through successfully. And now we're going to go to our second select, which is after the insert, which is this one. And you will see that this particular select, it has four results set that came back, and that's 6,000, 45,000, 5,000, and 33,000 that we just inserted now. And the overdraft of 10,000, entity 1, and account type 1, and the ID is 15 as auto-generated. So these basically went through successfully, and then if we look at the last select, which is after the commit, you will see the four rows or the 4 balances coming back as well. So you can see that everything that we did within this transaction, it conformed to the consistency. And before anything, when the insert failed to conform to the rules, the insert didn't happen. But as soon as everything ran through fine, then the transaction basically persisted as expected. So let's run it one more time. You just saw that I removed the default here. Let me just go back and remove it again. I removed this auto-generated ID, and I'm going to rerun this particular transaction again. Let's run that, and you will see that it violates a not null constraint, and the transaction fails because of that. So you can see that if any of the constraints that we have predefined are failing. So that is what we're talking about when we are mentioning consistency. So let me add this particular query under consistency, so that you also have it there when you are testing this within your database. So that looks fine. Then now let's go to isolation. So isolation is basically saying transactions are executed in isolation from one another. Even if multiple transactions occur simultaneously, each transaction must behave as if it is the only one happening. This prevents transactions from interfering with each other, ensuring data integrity. So isolation is, as you can see on my editor here, I have multiple transactions. I have the atomicity transaction, I have the consistency transaction, and I also have the isolation transaction, which is that one. And I then have the final transaction, which is durability transaction. And all these transactions, I can basically click a execute right here, and I will just say yes. It will go and execute all of these transactions, and it doesn't care whether there are other running transactions. And you can see it's executing all the transactions as it goes. It's executing all of them, and now it is done, and it's giving me all the stats. And remember, this is how many? 4 transactions, 1, 2, 3, 4, and it basically says updated rows 4. And basically the number of queries is 26, updated rows is 4, execution time is 162 milliseconds, fetch time 1 millisecond, total time 163 milliseconds, start time, finish time. And you can see this is the query stats for all the queries that were or all the transactions that were executed within this particular execution window. So all of these transactions, they execute in isolation as if none basically is executing at that particular time. So The durability transaction doesn't care if there's a consistency or an isolation transaction that is basically executing. It doesn't care about it. It executes as independently as it can execute. So that's basically what we're talking about in here. And there's a much deeper concept with isolation, because there's um, levels of isolation. So you can have, let's say, your dirty reads, you have read uncommitted or read committed data. So in isolation, there's isolation levels that you can basically specify for your transactions, and they will basically execute based on that particular isolation level. We'll dive deeper into isolation levels much later, but for now, I just want you to grab and grasp the concept of ACID principles within relational databases. And basically, this is what we're trying to achieve, to make sure that all our transactions can execute regardless of how many other transactions are running in parallel or simultaneously. So that is basically the responsibility of isolation, to make sure that in a multi-threaded or multi-purpose, multi-transactional database scenario, all the transactions can still execute without the hindrance and interference of other transactions in essence. So that's isolation in a nutshell. And now we are moving to durability. Durability is basically once a transaction has committed, the results are permanent. So the data is persisted into that particular database. Even if the system crashes immediately afterwards, the changes made by the transaction will persist thanks to measures like logging or backups. So things like this, your logging or your backups is what basically ensures that you can basically go back and review what was persisted and what was not. So in case of failures, any transaction that has committed, it has already persisted to the database and will basically stand the test of time. Even if there's a system crash or things like that, the data is already being persisted to the database, and everything is stored, and it can basically be recovered in that essence. So this is one piece that speaks to the atomicity of the ACID principles, to say is either the transaction will fully persist or commit, or it will fully fail or roll back. So the durability is the one holding thread that says, okay, this transaction has committed, therefore everything within this transaction has persisted, or this transaction has failed, therefore nothing has committed to the database, therefore everything else will be rolled back. And this is basically what speaks to durability, and you can basically interrogate the data after all the transactions, or in the case of system failure, when the system comes back, you can basically have a situation where you check all the data to make sure that all the transactions that executed, they executed as expected, and your data is consistent as much as possible. And basically, that is ACID principles in a nutshell. And we can basically add these transactions also for durability. Let me just add that one. Then for isolation, let me also add this one. So for isolation, you will see that there's a transaction. This transaction has an update and it has an insert. So you want to basically what we're showcasing here, that you can have a transaction that does an update and you can have a transaction that does an insert, all executing at the same time. There wouldn't be any impact. So this is what we're trying to showcase here, that you can have multiple transactions doing different things or doing the exact same thing, but because they are running independently of each other, therefore they cannot interfere with the execution of either transaction. So that is basically the premise of the isolation. And that's about it for this particular one. And until next one, for now, cheers.